Good morning, students. So today in the operating systems lab, okay, for the exercise 6, we'll be going through the implementation of deadlock avoidance algorithm, that is the banker's algorithm. So we'll look into the banker's algorithm. It's two main algorithms, that is safety algorithm and the resource request algorithm, and it's exact. Okay, so going on to understand, we'll first know what banker's algorithm is. Okay, so here a banker's algorithm in operating system, it is used to avoid deadlock and also for resource allocation safely to each process in the system. Okay, so as the name suggests, it is mainly used in the banking system to check whether the loan can be sanctioned to a person or not. Okay, so this banker's algorithm involves is a combination of two main algorithms. The safety algorithm to check whether the system is in a safe state or not, and resource request algorithm to check how the system behaves when a process makes a resource request. Okay, so we saw what a banking algorithm is. Okay, so what is banker's algorithm in operating system? So a process in the operating system can request a resource. So this can use the resource and can also release it. Okay, so here comes a situation of deadlock in operating system in which a set of processes is blocked. Okay, because it is holding a resource and also requires some other resources at the same time. Okay, so, this is being acquired by, which is being acquired by the other processes. So, at this point of time, a deadlock would occur. Okay. So, to avoid such a situation of deadlock, we have the banker's algorithm in operating system. So, banker's algorithm in operating system is a deadlock avoidance algorithm, and it is also used to safely allocate the resources to each process within the system without any occurrence of deadlock. So this was designed by Dijkstra. So as the name suggests, as we've seen, this banker's algorithm, which has been used in the banking system, okay, is used to identify, like using the information and the data given by the person to be used to identify whether this loan should be given to a person. Okay, so this process, when implemented in operating system, it will be decided if whether it is what is a safe state or not, and so on. Okay, so we've seen what a banking algorithm is, what a banking algorithm in operating system is. So I'll just give you a comparison of a real world scenario, and let's see how so that you can understand what really happens with the operating system. So we can just take it as we have suppose like n account holders in a bank, okay, and the total sum of their money is X, okay. So if the person is going to apply for a loan, okay, then the loan amount subtracted from the total amount available in the bank gives us the remaining amount, okay, and that amount should be greater than X, okay. Only then the loan will be sanctioned in the bank. So it is done with keeping in mind that in any worst case scenario where all the account holders would come to withdraw the money. Okay. This is the worst case scenario. Okay, it's not a common scenario which happens every day, but they've taken the worst case scenario as if every account holder comes to withdraw their money from the bank at the same time. Okay, so thus following this banking system, they would be able to always remain in a safe state. Okay, so this is applied in operating system. Okay, how is it applied? Banking algorithm that works similarly. Okay, like here we have process. Okay, each process within the system must provide all the important necessary details to the operating system, like upcoming processes, requests for the resources, delays, etc. So based on these details, OS will decide whether to execute the process or to keep it in a waiting state, okay, which would avoid a deadlocks in the system. Okay, so thus a banking algorithm is also known as the deadlock deduction algorithm. So I hope you're able to understand the comparison between banking algorithm in a real world scenario and how it is implemented in the operating system. Okay, so we have gone through the concept. So let's just go for the algorithm, how it's implemented, their terminologies and everything. Okay, so following with the data structures are used here to implement the banker's algorithm. So N is considered as the number of processes in the system, and M is the number of resources types. So we have available the maximum, the allocation, and the need, and all the required process details. Okay, for available, it is a 1D array of size M integrating the number of available resources of each type. And here K means there are K instances of resource type Rj in the available column. Okay. For maximum, it is a two-day array of size n cross n that defines the maximum demand of each process in a system. So here K means process of PI, which may request at most K instances of resource types of RJ. Okay, and for allocation, it is a two-day array of size n cross n, which defines the number of resources of each type currently allocated to each process. So for its allocation, your K means process PI is currently allocated, where K instances of resource type RJ. Okay. And for need, it is a two-day array of size n cross n that indicates the remaining resource need of each process. Okay, for where K means process PI currently needs K instances of resource type Rj. Okay, where for need to find the need, you will have to minus max minus allocation. Okay, so allocation I specifies the resources currently allocated to process P, and need specifies the additional resources that process P may still request to complete its task. Okay. So banker's algorithm consists of safety algorithm and also resource request algorithm. So now we look at it. Okay. So here we'll see the important data structure terms which will be used in implementing banker's algorithm in operating system. So here, like you saw, available, max, allocation, need, and the finish example. Okay. Here we saw for available, okay, the key instances of resource type Rj are available within the system. Okay. For the max, the K will indicate the process speed and it will request for maximum key instances of resource type Rj within the system. And for allocation, the K will indicate the current process PI. Okay, which is allocated to the key instance of resource type Rj, which is within the system. For need, the K will indicate the process P, which presently requires key instances of resource type Rj for its execution. So the finish example, okay, here for the finish, the true will indicate that process P has been allocated all the required number of resources by the system. Okay, so while implementing or like working with bankers algorithm in US, you have to know three things, okay, three main things. That is how many resources of each type a process can request for, and which will be denoted by max array. Okay, and how many resources of each type process is currently holding or allocated, it will be denoted by allocation array. Okay, and then how many resources of each type are currently available within the system. This will be denoted by the available array. So these are the three main things which you have to keep in mind. So let's go to the safety algorithm. That is, this is the algorithm used for finding out whether or not the system is in a safe state. Okay. So this is the algorithm for safety. Okay, so we have work and finish, okay, where the vector lengths are taken as m and n respectively. We initiate the work, okay, and as it goes on, we will have to find out the final output should be that we will have to find out using this algorithm, we should find out if the system is in a safe state or not, okay. You will be using this algorithm to implement your programs based on safety algorithm. So let's look into have a deep section on safety algorithm. So safety algorithm in operating system is used to mainly check whether the system is in a safe or not, safe state or not. Okay. So to that you will be following certain steps. Okay. The first step here is that the algorithm for C that we have seen. Okay. The algorithm C is all about the safety algorithm. We need to use a finish array of size n. Okay. That is for each process that stores value of 1 if all the resources have been allocated to a process otherwise 0 as a resultant value. Okay. So next what we need to do is we need to check which process hasn't been allocated all the resources yet. Okay. With the condition provided that the need of high will be less than or equal to available for that process. Okay. And you should also know that if such an index or the process doesn't exist, and the needs resources from the available array, you should go to step 4 directly. Okay. And the third step would be if resources have been allocated to a process, we need to update the available. Okay. And finish the array. That is the available to final array, you should add available and the allocation of it. Okay. Getting new to get new resource allocation. Also, where we consider the finish value, which is equal to 1 for the currently allocated process. Okay. And you should also know that to go to, like you go to step 2 for checking the status of, you should go to step 2 for checking the status of resource availability for the next process to follow it. And the last one is to be to finish. Okay, when you completed everything, your value will be 1. Okay, so then you will know that the system is in state, a safe state, or not. Okay, so these are the steps to follow when you're going to find out if a system is safe or not. So next we'll move on to the resource request algorithm. So here, this is the algorithm for resource request. Okay, we'll be using this for your programs. Okay, so to find out what you see, okay, that you like for to find out for available, you have to minus the values available minus request, and for allocation you'll be adding allocation plus request, and for need you'll be we will need minus request value. Okay, all these are to see that to have a system pretend to have allocated the requested resources to process by modifying the state. Okay, to modify the state, we'll be doing the following for available, allocation, and need. Okay. So here we look through the steps for the resource request algorithm. That is, the resource request algorithm would check the behavior of a system. Like whenever a particular process makes a resource request in a system, it will mainly check whether a resource request can be safely granted or not within the system. Okay, so this algorithm takes the following actions upon receiving a resource request from a process P. So this request would be the request array for the process. Okay, whereas for the request here, the K would mean the process needs K instances of resource type RG. Okay, so we'll begin with the steps. Okay, for the step 1 for the request, the need, okay, that should indicate that the requested resources are less than equal to the need matrix resources for that purpose. Okay, so we go to step 2 immediately, or else an error would be generated because a process is requesting more resources than the maximum resources that can be allocated to that process. Okay, and for step 2, okay, the request, okay, to make it available, it should indicate that the requested resources are within the range of available resources, okay, which are currently present in the system. And when you go to step 3 immediately, the process speed will wait, okay, because the required number of resources are not available at present, okay. And for the step 3, we're going to assume that the request has been granted and resources have been allocated to the desired process, okay. And the next thing is we need to modify the states, okay, that is available. You'll be doing it with a given request. For available, you have to do available minus request. For allocation, we'll move with allocation plus the request. And for need, we'll go for need minus the request values. So This is your first example, okay? So here we have a process table with number of processes, PO, P0, 1, 2, 3, and 4, okay? These contain allocation fields, okay? Why do they contain allocation fields? To show the number of resources of type, okay? A, B, and C, which allocation. So each process has an allocation table allocated to it, okay? And also a max field, okay? Why is the max allocated? To show the maximum number of resources of type which belongs to A, B, and C that can be allocated to each of its respective processes. And also that the available field, okay? What does it mean? It means that it is given to show the current availability resources of each type in the table. Okay, so when a table as such is given, you will have to understand the processes. Processes would be there. Okay, and why do we have allocation? Why do we have the max field? And why do they have the available field? And how is the available field calculated and everything? You should know. Okay. So considering the above processing table, we'll calculate two things. Okay, the first one is the need matrix. Okay, and the second one is to find out if the system is in a slave state or not. Okay, so using the need matrix, using the formula, we're going to find out the need matrix value. Okay, so I've told you the formula for it. That is need is equal to max minus allocation, and so using that, you'll be able to find the values. Using which you'll be able to find the value for need. Okay, so the values are given here. You can calculate it manually and you can check it. Okay. So next is you're going to check for your safe sequence. How would you be able to do that? For a process PO, okay, you have a need and your availability. Okay, so clearly the resources needed are more in number. Okay, you can check with the numbers. The need is 4. Okay, but the availability is 3. Here it's the need is 3, but the availability is 2. Okay, so we lack one slot. Okay, for each of the processes we lack. So we need one more in number than the available ones. So now the system will move to process the next request. Okay, so for process P1, the need is 2, 2, and 1, and the available is 3, 2, 1. Clearly, here too, the resources are less than equal to the available resources within a system. Hence, request of P is P1 will be granted. Okay, the process PO had like more number of availability, more number of it had its need was more, its availability was less. So it was whole. It was kept in whole. And then moving on to P1, okay, the same thing continued, but then the need was less. Compared to process 0, process 1's need was less. So hence the request of P1 is granted, okay. And coming to, so to find out availability, the word available plus allocation to get your new available, okay. So now for process P2, okay, it follows for both process P2 and P3, the same follows, okay. Okay, so the same goes with process P4. Now again, okay, after your P4, what happens? You went for P0, P0, 1, 2, 3, and you come back to 4. You went to 4, and then you again go back to P2, right? And you find out that the resources needed are less than equal to the available resources within the system. So now request of P2 is granted. Okay. Before was it granted, you should verify, like process by process. Okay. Next, we'll be moving on to again to process 3, then to the process 0. Okay, where you'll be able to find out, finally you'll be able to find out the safe sequence. Okay, then you'll be able to understand that the system has allocated all the required number of resources to each process in a particular sequence. So therefore, its conclusions would be, when you've gone through all the processes, okay, your conclusion for this example is that it is proved that the system is in a safe state. Okay. So this is your example 2. Okay. Here we can have 5 processes. We have 5 processes. It's allocation. Okay. So the PO through PO and 3 resources of type A, B, and C. So resource type A has 10 instances. Okay. And B has 5 instances. And type C has 7 instances. So suppose at time T0, okay, T0, the following snapshot of the system has been taken, okay, and you are going to find the need matrix as a see if it's whether it's in a safe state or not, okay. They're going to use the same formula, okay, and you're going to find out the need has been found out, and process by process. Okay, like we saw earlier, the safety algorithm is being applied, and you're trying to find out the sequence. Okay, and if suppose the true for zero is less than I, which is also less than n. Okay, so this is the final value you should get. Okay, so that you know that the system is in a safe state. Okay, so hence the sequence of for this is P1, P3, P4, P0, P2, and hence the values are the same, we'll be able to tell that the system is in the safe state. Here we have another thing, like what will happen if process P1 requests one additional instance of resource type A and two instances of resource type C. Okay, so they'll have to decide whether the request is granted to use resource request algorithm. Okay, so here we must determine whether this is new system state is safe. Okay, so what happens here is again they will have to the same values. We are here to find out using the resource request algorithm. But then since the system safety is under question, okay, again they will have to execute the safety algorithm using the above values, okay, and then it will be followed with the resource request algorithm. So here, finally, it is found that this is the new system which has been found is safe. So the grant request for the process P1 code for the banker's algorithm is what is processed. So your expected outcome, okay, from out of all this, you've got your sequence, okay? You get your sequence, you know that your system is safe. What are your expected outcomes out of it, okay? So as the processes enter the system, okay, they must predict the maximum number of resources needed, which is not impractical to determine, okay? And in this algorithm, the number of processes remain fixed, which is not possible in interactive systems. And also this algorithm requires that there should be a fixed number of resources to allocate. If a device breaks and becomes suddenly unavailable, the algorithm would not work. So, and overhead costs incurred by the algorithm can be high when there are many processes and resources, because it has to be invoked for every process. Okay, because they're trying to call out for each process, the overhead cost will be definitely high. Okay. So here there comes a situation of deadlock universe in which a set of processes is blocked, okay, because it is holding a resource and also requires some other resources at the same time that are being acquired by other processes. So what happens with this banking algorithm and operating system would use here is used to avoid such deadlocks, okay, and also for resource allocation safely each process in the system. And for bankers algorithm, which is mostly used in the banking systems to identify whether the loan should be given to a person or not, there are some important data structure terms, okay, which are used to implement bankers algorithm in operating system, which are like we saw earlier, available max allocation, need and finish, okay. So I'll give a fast run through the summary of all the important terms and everything we have discussed as far. So here the banking algorithm consists of two main algorithms, safety algorithm and resource request algorithm, which are used to avoid deadlock and to control the processes within the system. So here safety algorithm in operating system is mainly used to check whether the system is in a safe state or not. Resource request algorithm checks the behavior of a system whenever a particular process makes a resource request in a system. It mainly checks whether resource request can be safely granted or not within the system. The disadvantage of the banker's algorithm in OS is that it doesn't allow a process to change its maximum need of resources while processing. And all the processes within the system must know about the maximum resource needs in advance. So the banker's algorithm in US requires a number of processes for processing, and no additional process can be started in between. So the banker's algorithm, this is the reason why it is also called as the deadlock reduction algorithm. And when somebody tells you deadlock reduction algorithm, it purely means that they are pointing out on the banker's algorithm. So I hope with this content and the examples that you have discussed, you have a good idea about banker's algorithm and will be able to complete your objective of this exercise.